Today, we're very pleased to have Zaher Hani from the University of Michigan, who will talk to us on Hilbert's sixth problem for nonlinear waves. And I believe this very interesting and well-regarded work is in joint with Yu Deng.
All right, indeed. Okay, yeah, so as Susan said, everything that I'll be talking about is wouldn't have been possible for your distinguished colleague, Yu Deng. Okay, so focusing the board here. I probably you wouldn't like it to show up this way, but I believe there's a way to view the window as full screen. Old method. This should work now. Yeah. Oh. Right. It's not quite optimal, is it?
Yeah, it was showing enter full screen. That one should be the right one.
Maybe put on one side.
Enter full screen, yeah.
Yeah, it looks good.
Yeah, no.
Make it this way, then.
Yeah.
Is it better now?
Yeah.
Okay, perfect. Okay, so here's the outline of today's talk. I'll first discuss a little bit what Hilbert's sixth problem is in its classical context, which is the particle context. And then we will discuss what this sixth Hilbert problem means for waves. And I will tell you what this will lead us into a theory that often goes by the name of wave turbulence theory. Then we'll start talking about some mathematical results. So let's start talking about Hilbert's sixth problem. So this is one of the problems that Hilbert listed in his 1900 ICM lecture. And what it asks for an axiomatic derivation of the macroscopic laws of physics, mainly statistical physics, from the microscopic laws of dynamics. So let's see what this means. First thing to remember is that those statistical laws, they govern macroscopic variables like temperature, pressure, fluid velocity, and typically they are irreversible in time. So here you think of the second law of thermodynamics, which tells you that entropy increases in the forward direction of time. On the other hand, the dynamical laws, which are the things that we want to take as axioms in order to derive the statistical laws, those are laws that govern microscopic quantities like particle trajectories and orbits. And they are typically reversible in time. There's no preferred direction of time in Newton's equations. There's no preferred direction of time in Hamilton's equations. So part of the question that has to be answered in or within Hilbert's sixth problem is this: how does this arrow of time emerge? How does statistical physics laws pick a preferred direction of time or a forward direction of time and a backward direction of time, something that is not present in the fundamental laws? So in 1902, Hilbert got a little bit more specific about this problem because it's in its original formulation, it was fairly broad. And in this specification, he suggested looking at the problem of developing mathematically the limiting process that goes in Boltzmann's kinetic theory. So this limiting process can be depicted in the following diagram. So in Boltzmann's kinetic theory, one starts with a system of n-colliding particles that are obeying Newton's laws. Then one passes to a kinetic limit under which one gets to a mesoscopic scale, which is governed by Boltzmann's kinetic equation. And then there's another limit that is involved, which is called the hydrodynamic limit. And under this limit, you get your favorite fluid equations, compressible Euler. And from compressible Euler, you can get Euler's incompressible Euler and the incompressible Navier-Stokes equation. So Boltzmann was interested, and Hilbert himself also was interested in justifying this passage from Newton's laws all the way to those macroscopic equations, the hydrodynamic equations. I should mention here, I won't talk too much about the second arrow in this diagram. It's considerably much more understood than the first arrow. This is thanks to works of many, many people. I picked up a representative of those works by Dimansi, Esposito, and Leibowitz, which dealt with strong solutions, and Gauss and San Remo in 2011, which is a work on weak solutions, conversion of weak solution of Boltzmann to weak solutions of Navier-Stokes, for example. Okay, but I won't talk about this limit much. The main challenge really comes from this kinetic limit, and the challenge of justifying giving what Hilbert called atomistic view of the laws of motions of continua. The main challenge is really in justifying and understanding this first arrow. So let's try to look a little bit into this arrow. So this is Boltzmann's kinetic theory. As I said, the starting point is a system of n particles, each having a radius r, and those particles are undergoing elastic collision, much like air particles in this room right now. And the initial states of the particles are assumed to be random and independent, so that I can talk about each particle having an initial density f naught of xv, which you can understand as the probability of finding a particle at position x moving at velocity v. Okay, and the fact that this f naught of xv is the same for every particle is the assumption of independence. And then what the Boltzmann was interested in is he was interested in deriving an effective equation for the one particle density, f1 of txv, which you can think of as the probability of finding a particle at time t at a position x and moving at velocity v. And Boltzmann's ingenious contribution is that he found an effective equation for this one particle density, which we now call Boltzmann's equation. And it's, I write it to you over here. So there's a transport term on the left, dTv plus v dot grad f equals to what is called a collision kernel, which is a quadratic collision kernel that I write below. I write it, most of you have seen it in a different form, at least for the integral, for the sort of the measure on which you integrate this f1, f3 minus f2, but its equivalent can be written this way, and I write it this way because I want to draw a parallel with what we will be talking about for waves. Okay, so you're basically integrating over velocities v1 plus v3, velocity v1, v2, and v3, so that satisfies v1 plus v3 is equal to v plus v2, and you have also the restriction that v1 squared plus v3 squared is equal to v2 squared plus v squared, which is the conservation of energy at the collision. Okay, so what we want to do is that we want to start from Newton's equations for n particles and give a rigorous derivation of this Boltzmann kinetic equation. And this has been done for short times, thanks to works of a lot of people, starting mainly with works of Lanford, King, and several others that completed and filled some gaps in Lanford's proof. So this is what we call now Lanford's theorem. This short-time justification is now called Lanford's theorem. And what it says is that in the limit as the number of particles goes to infinity, in the limit as the radius of the particle goes to 0, and under a particular scaling law, which links how those limits are taken, basically this scaling law is called the Boltzmann grad scaling law, in which n goes to infinity and r goes to 0 in such a way such that n times r to the d minus 1 is order of 1. Then the following two things hold. The first thing is propagation of chaos, which tells you the following. So remember, I told you that at time t equals to 0, the states of the particles were random and independent. So what this propagation of chaos statement is saying is that those particles, because they are colliding at later times, of course, they lose their independence. But somehow, magically, in the limit, in this kinetic limit, n goes to infinity and r goes to 0, this independence is retained. It re-emerges once you take the limit. It's definitely false before you take the limit, but it re-emerges once you take the limit. So this is a very deep statement, and in some sense, it is really the heart of the matter, this propagation of chaos. It was an assumption done by Boltzmann, but if one wants to prove Lanford's theorem, this assumption needs to be proved. And once you have this propagation of chaos, you can justify Boltzmann's equation and the fact that it appears as the effective equation for the one particle density. And what this statement is that the one particle density converges to the solution of the Boltzmann equation for sufficiently small times. Unfortunately, despite the fact that, despite several developments over the past 50 years, this small time restriction has not been lifted. And it's basically, this is the reason, and Hilbert's sixth problem reduces to this question, basically giving a proof or giving a version of Lanford's theorem for long times. This is very much one of the biggest open problems in kinetic theory. All right, so this is what will lead us to looking at the wave version of this problem. Next. So Hess theory-wise, this theory, this is what we will call the wave kinetic theory. So this is basically trying to develop a theory of a kinetic theory similar to that of particles that was developed by Boltzmann in the context of waves. And this was done at the turn of the last century, basically around the 1920s. And there was quite a bit of motivation in order for physicists in order to develop such a statistical theory. So this was first done by Peirce in 1929, who wrote down the very first wave kinetic equation, and in the context of understanding vibrations in crystals. Okay, so this is the wave kinetic equation for anharmonic crystals. Then shortly after, the second wave kinetic equation emerged by the works of Nordheim and Ulling and Uhlenbeck, who were basically considering essentially the same system as Boltzmann, except that the particles, rather than being classical particles that are governed by Newton's laws, are now quantum particles that are governed by the many-body Schrödinger equation. And in that context, what you obtain is something that is often known as the quantum Boltzmann equation. Sometimes it's called Nordheim and Uhlenbeck equation. Then in the 1960s, Hasselmann applied this formalism of wave kinetic theory to the context of water waves, and this led to a lot of developments, and particular developments in the field of oceanography, very much linked to wave kinetic theory. Then also in the 60s, Zakharov and his school really sort of generalized this formalism to be able to apply it to very general dispersive systems. And his most important contribution was discovering a strong connection with this wave kinetic theory and Kolmogov's theory of hydrodynamic turbulence. As it turns out, that Zakharov discovered that the energy cascade phenomena for wave systems can be understood using this wave kinetic theory and using those wave kinetic equations. And if you use that, you get conclusions that are very similar to those that were obtained by Kolmogov using scaling considerations mostly. So these, for example, one obtains power type spectra for the energy cascade, and those appear as stationary solutions of the wave kinetic equation in this context, rather than coming from scaling considerations. And those spectra came to be known as the Kolmogov-Zakharov spectra. And it is why this theory is called wave turbulence theory sometimes. Okay, I won't be addressing any aspect of this, any turbulence aspect of this theory today, but this is definitely something that is a big motivation for us, and it's something that is really underlying a lot of the things that one would like to do in the future. But we'll get to that maybe on the last slide. So what is the formalism of this wave kinetic theory? We'll try to really stick to this parallel to Boltzmann's theory. So here we have a microscopic system. Instead of the microscopic system being formed of n particles that are colliding, now this microscopic system is replaced by interacting waves. And these interacting waves could be, for us today, they would be understood as the Fourier modes which are plane waves, essentially, colliding with each other in a large periodic box of size L. In an inhomogeneous setting, which I will not be discussing today, those Fourier modes would be replaced by wave packets that would also be essentially thought to be interacting with each other or colliding with each other. So today we will focus on the homogeneous setting. The microscopic dynamics, rather than being given by Newton's equations, now the microscopic dynamics is given by the solutions of a nonlinear PDE, more precisely a nonlinear PDE of wave type or dispersive PDE. Okay, where the strength of the nonlinearity, we will call it alpha, and this strength of the nonlinearity will replace the radius of the particles in Boltzmann's theory. Okay, so the thermodynamic variables, you might have guessed them now. So instead of thinking of number of particles going to infinity and the radius going to 0, we will think of a system size L going to infinity. The system size L is very much linked to essentially the number of waves that are available and interacting with each other. And the other parameter that will replace R is this interaction strength alpha, which will go to 0 in the kinetic limit. Okay, so for many reasons, we will, the nonlinear Schrodinger equation is the prime example for this theory, and we will adopt it for the rest of the talk and for our work. So this is written in front of you if you haven't seen it before. So you have the linear Schrodinger equation on the left-hand side. On the right-hand side, there's a cubic nonlinearity, and as I told you before, we will index the strength of the nonlinearity by this parameter alpha. We will pose this equation on a periodic box of size L, which will diverge in the limit, and we will stick to dimensions d greater or equal to 3. Just like in the Boltzmann picture, remember the limits n and r going to infinity and 0, we're not taking arbitrarily, but according to the Boltzmann grad scaling law. So the same thing happens here. The limit L and alpha cannot be taken arbitrarily. There needs to be a scaling law that is sort of governs this limit. And the scaling law has the general form of the scaling law would be alpha equals L to the minus gamma, okay? Where gamma could be anything between 0 and infinity inclusive. But it turns out that due to some number theoretic considerations that I don't want to get into here, there is a range of admissible scaling laws in this case, which is gamma between 0 and 1. And this is the range of scaling laws where you really could expect a wave kinetic theory. Okay, it's interesting that in this homogeneous setting, there's a range of scaling laws as opposed to in the Boltzmann picture where there was just one scaling. Okay.
What does admissible mean in this context?
Admissible means that this is the scaling. This is a scaling law for which you expect the kinetic theory to emerge. Okay, outside the scaling law, you really do not expect the kinetic equation to emerge. You cannot expect to build a kinetic theory similar to that of Boltzmann's, okay, which I will describe to you next. The next analog that we need to precise is the randomness of the initial data. So just like in the particle picture as well, we have to adopt a random distribution of initial data, which we can describe in this wave version of things as follows. So we basically take the initial data for the nonlinear Schrodinger equation to be a random variable, which is given to you as follows. So this is the first equation here is just the expansion of the initial data in its in Fourier series. So remember that since we are working on a box of size L, the Fourier domain is the lattice of mesh L inverse. So it's the lattice L inverse ZD. And the randomness is described in the second equation here, where we are saying is that the Fourier modes is given as follows. The modulus of the Fourier modes, or the absolute value of the Fourier modes, is given by the square root of an initial of k, where an initial of k is a non-negative, sufficiently nice function. And then I randomize the phases by multiplying by a Gaussian, or not necessarily Gaussian, just a for the sake of formally stating the theory, IID normalized random variable. In other words, their mean is 0 and their variance is 1. We call such data well prepared because the Fourier modes are independent because those eta k are IID for different k's. And you have that if you look at the modulus squared of the initial data, modulus squared of the initial data in Fourier space, this is given by this function an initial of k. This an initial of k will be the initial data for the kinetic equation that will show up. Okay, and of course, the goal of the wave kinetic theory is to start with this random initial data and to be able to describe the distribution of the Fourier modes at later times in the limit of large L and small alpha. And the central quantity, just like the central quantity in the Boltzmann picture, was the distribution of the one particle distribution. Now the central quantity is the variance of the Fourier modes, the expected value of U hat squared. So here's the kinetic conjecture. it says the following. It says in the limit as L goes to infinity and alpha goes to 0, the following holds. First, you have propagation of chaos. Again, you want to emphasize that this is a very deep and nonlinear statement. So you are starting initially at time t equals 0 with Fourier modes that are random and independent. Once you turn the nonlinear interaction on, those Fourier modes start interacting with each other. And of course, they lose that independence. But the deep statement that is being said here is that if you take the kinetic limit, L goes to infinity and alpha goes to 0, this independence is retained. But again, not before taking this kinetic limit. Again, you have a kinetic equation that governs the effective dynamics of the variance of the Fourier modes. And now this kinetic equation is called the wave kinetic equation, which I will write for you on the next slide. And it has to be rescaled to the what is called the kinetic time, which is 1 over alpha squared. Alpha is the strength of the nonlinearity. More precisely, what we expect is that if you look at the variance of the Fourier modes, that this is given by the solution of the wave kinetic equation at time t over t kinetic, plus an error that goes to 0 in the limit as L goes to infinity and alpha goes to 0. Okay? So of course, U is the solution of NLS, N is the solution of the wave kinetic equation. And the third thing in this conjecture is that not only you can describe the variance of the Fourier modes, but you can also give a precise picture of the higher moments and maybe even the limiting behavior of the density or the low of the Fourier modes. Okay, so I still owe you the statement of the wave kinetic equation. This wave kinetic equation is given by dTn is equal to now we have a cubic collision kernel rather than a quadratic one. The initial data that you solve the wave kinetic equation is n initial, the same n initial that appeared a couple of slides ago. Okay, and now you have a collision kernel that, as I said, is cubic, but notice that the measure on which you are integrating is exactly the same measure that appears in Boltzmann, and this is just because you are dealing with Schrodinger equation. If you change the Schrodinger equation into something else, then you'll get a different integrand over here. But this is part of the importance of the Schrodinger equation, that it shares the same measure of integration as the Boltzmann equation. Of course, the integrand is a little bit different. It is cubic rather than quadratic, and it's given to you over here. Okay. There's an inhomogeneous version of this equation where one has to start with an inhomogeneous setting rather than the homogeneous setting that I described to you, or it started on a torus of size L, where the initial distribution was really independent of where you are in space. Okay. So if you look at the covariance of the initial distribution, it only depends on the in physical space only depends on x minus y rather than depends on x and y itself. So that's the homogeneous version. But one can look at the inhomogeneous version of this wave kinetic equation, and in that case, you would have a transport term on the right hand side. Okay, we took a very first step in the analysis of the inhomogeneous equation in a work of with Chapin and Su. So this is indeed a wave analog of Boltzmann's equation, and I already pointed out the relation to Boltzmann's equation. One also can point out the relation to the quantum Boltzmann equation, which is the equation that I mentioned briefly before as one of the earliest wave kinetic equations that was written. So interestingly enough, the quantum Boltzmann equation can be seen as it's actually just a linear combination of the collision kernel there is just a linear combination of the Boltzmann collision kernel and this collision kernel over here. Yeah.
Can you go back to the previous slide? So for the second point, when you say the dynamics is given by the equation you just showed, what's the time of existence for it?
Yeah, this is a good question. So it's really so basically the precise statement of the effective dynamics being given by the wave kinetic equation is contained in this equation that is called approx. And what you want is basically to prove this on a time interval where the solution of the wave kinetic equation starts to show up. So basically, you want to get to times ideally, if you want to state a physical conjecture, you want to get to times that are multiples of the kinetic time over here. So you want this to hold for times between 0 and multiples of the kinetic time. Because if you're much smaller than that, then the solution of the wave kinetic equations really did not have time to exhibit itself.
So
Is that your answer?
when we are taking alpha to 0, how does it work with time being multiples of kinetic time?
Right. So as alpha goes to 0, this time becomes larger and larger. So the way to resolve this is to think of this as a finitary statement. Okay, that this is a statement for small alpha and large alpha.
So in the limit, dynamics is given for globally in time. Can you say that?
It's given for the Schrodinger equation. It's given for up to multiples of the kinetic time. So very, very large multiple, very large times. Okay. So the right way to think about it is to think about it in a finitary way. That this is basically a statement for times that are multiples of 1 over 2 alpha squared. And you're saying that this dynamics is equal to this dynamics plus something that is very small if alpha is very small.
I don't think there is like a fixed limits dynamics or fixed limit equation. It's an equation put on a torus of size L, so you cannot directly talk about its limits.
Right.
For example, like with the particle system, there are n particles. You cannot say you don't have a limit which is dynamics with infinitely many particles. So you need to talk about that set.
Precisely because that restriction n times r to the d minus 1 is basically a restriction on the diluteness of the gas. So if you let n go to infinity and you want the gas to stay dilute, then there is no system for which n can be taken to be equal to infinity. So what Yu Deng is telling you is that there's not only a problem with thinking of this when alpha goes to 0, but even when L goes to infinity, there's a problem of thinking about this exact limit L to infinity. But the way to think about it is in the finitary way that I mentioned. Okay, is there anything else? And again, this is a kinetic approximation. So there's a passage from something that is time reversible, which is the nonlinear Schrodinger equation, into something that is time irreversible, which is this kinetic equation that has an entropy and this entropy grows in the forward direction. Okay, so let's talk about some background mathematical results that are related to this, of course. So there's, one should mention the work of Hilbert, Fraunhofer, and Yau, which they dealt with the linear Schrodinger equation with the random potential. So over there, the reason why this is related to it is that over there also there is a kinetic equation that one would like to justify, and one would like to approximate the dynamics of the linear Schrodinger equation with the random potential to that of that kinetic equation. And this was done by Hilbert, Fraunhofer, and Yau, and even they were able to go well beyond of that kinetic time because they are dealing with mainly because they are dealing with the linear equation. So the first work that dealt with a nonlinear equation, which was a work of Lukanen and Spohn, as opposed to the scenario that I described to you over the previous slides. Lukanen and Spohn were studying a similar problem, but at a statistical equilibrium. What this means is that they were basically taking initial data that were distributed according to a Gibbs measure, and the Gibbs measure is invariant under the dynamics of the equation. Okay, so they were interested in the time correlate, the evolution of the time correlations of those Gibbs measure, which is a related problem. It's nonlinear, but it is at a statistical equilibrium. The first work to deal with the full nonlinear problem was work of Buckmaster, Germain, myself, and Chata in 2017. So there we were interested in the problem of justifying and deriving this wave kinetic equation, but we were in the setting, we put ourselves in the setting of an irrational torus. This is not the important restriction. The important restriction or the important drawback of that work is that we really weren't able to get too much close to the kinetic time. Our times of approximation were things like kinetic to the 1/2. So that was highly optimistic. And then this was the first time that we started our collaboration with Yu Deng in 2019. And we were able to improve this approximation all the way to timescales that are of the form T kinetic to the 1 minus epsilon, where epsilon can be arbitrarily small but positive for some scaling laws. Independently, there was work of Collin and Germain around the same time that did essentially the same thing. But all those works should be viewed in a were a little bit unsatisfactory, is that because all of them failed to reach the kinetic time. Okay, so remember in this approximation over here, we really would like T to be some multiple of the kinetic time, at least a small multiple of the kinetic time, so that you can see the variations of the solution of the wave kinetic equation. Okay, and this would what a full justification of the wave kinetic equation would be doing, which would be similar to Lanford's theorem that did a similar thing for Boltzmann's equation. So this brings us to the first main result, which is this first main result is by now not so new. So this was done in a joint series of works with Yu Deng since 2021. And in those works, we were able to give a full mathematical justification of wave turbulence theory at the kinetic time. So let's read the statement slowly. So we consider an LS on a periodic box of size L in dimension d greater or equal to 3. We take any initial to be the initial data of the wave kinetic equation. So this is non-negative. I mean, this is an overkill saying that needing it to be Schwartz function. You just need it to be sufficiently smooth and decaying. And we take initial data for the nonlinear Schrodinger equation to be well prepared, as we described a few slides ago. So you had of k is given by square root of any initial times those IID random variables, which basically all you need from them is that they are rotation symmetric and have exponential terms. You can think of them as Gaussian. And in terms of scaling laws, we have alpha is like L to the minus gamma, where gamma could be anything between and the interval 0, 1. And recall that the kinetic time is basically 1 over alpha squared. Then we have what you expect. There exists a delta and an absolute constant nu, such that for L large enough, you have that the expected variance, value of the square of the Fourier modes. Okay, so here I put the T kinetic over here, at times T times T kinetic is given by a solution of the wave kinetic equation plus something that goes to 0 as L goes to infinity. And this holds uniformly for T between 0 and delta. Okay? And this delta is basically a fixed constant. And N is the solution of the wave kinetic equation with initial data and initial. So this theorem is a combination of several works. The first work was done in 2021, actually, here. It appeared in 2023, but it was done in 2021, where we basically give, which corresponds to this theorem when gamma is equal and close to 1. Then we had another paper where we justified the propagation of chaos and studied higher order moments. And then in a third paper where we covered the full range of scaling laws, gamma between 0 and 1, okay, which was appeared on arXiv about a year ago. We also have an explanatory paper if you're interested in reading a little bit about this theory without going too much into details. Okay, so the conclusion is that this provides a full mathematical foundation of wave turbulence theory by answering the 3 questions that I listed in the conjecture: the propagation of chaos, the kinetic equation, and even the evolution of the limiting densities. Those things, propagation of chaos and the evolution of the limiting densities, are not things that I stated in the theorem, but we have theorems for those things as well. Okay, and the conclusion of this is that we have reached at the end of those works a level of basically the level of progress in the particle kinetic theory. This is basic, you can think of them as Lanford's theorem in a wave setting, okay, where we justify the kinetic equation up to small multiples of the kinetic time. Okay, what we did in recent work that we posted on arXiv in November of last year is that we were able to push the wave kinetic theory beyond the particle theory. So now the state of the art in the wave kinetic theory is actually beyond the state of the art of the particle theory, because we are able to extend the derivation of the wave kinetic equation to arbitrary long times. And this is the first long-time result in any nonlinear kinetic setting. So the statement of the theorem now can be done in a very simple way. The same assumptions as in theorem 1, but the justification of the approximation of the NLS dynamics, which is the variance of the Fourier modes, and its approximation to the solution of the wave kinetic equation holds for arbitrary long time interval 0 t star. The only condition over here is that the solution of the wave kinetic equation exists on this interval 0 t star. Okay, which is basically the minimum that you can assume. Sorry.
Do you need uniqueness?
Yes, I mean, we need that the solution is sufficiently regular on this interval 0 t star, and in this class of sufficiently regular solutions, the solution is unique. So in the remaining minutes of the talk, maybe 15 minutes, let me tell you a little bit about the proof. Okay, so I can tell you about the long-time proof before discussing the short-time proof a little bit. So all proofs, essentially all proofs where you derive or justify a kinetic equation, these are all based on diagrammatic expansions. This is an idea that was proposed by Feynman in 1948 in order to keep track of basically perturbation expansions. So whenever you are trying to do a perturbation expansion, a good way to do it is by using those diagrams. And this was an idea that was quickly adopted in the math physics community. It was a very good idea. So basically here you start with the solution of the nonlinear Schrodinger equation, of course, and you expand it in terms of its Picard iterates or Duhamel iterates. You don't keep on expanding indefinitely. You just stop the expansion at maybe a very large parameter n that we will have to choose very wisely later on, and then declare everything that is rest as a remainder. Now, the idea of those diagrammatic expansions is that each of those iterates, un, can be represented as sums of diagrams, and in this case, they are sums of ternary trees with n branching nodes. So the number of branching nodes of a tree would be called the order of the tree. So for example, this is a tree over here. This is a tree of order 3 because it has 3 branching nodes. And this is something that appears in the third Picard iterate of the cubic nonlinear Schrodinger equation. But I'm looking at the variance. I want to look at the variance of the Fourier mode. So this is the expected value of u hat bar. Okay, so I have 2 copies basically of the solution. Okay, u and u bar multiplied with each other. And so I get, this gives me 2 trees that are basically multiplied with each other. What it means to be multiplied with each other, because of this expectation over here, you should think of the leaves of those trees to be completely paired with each other. So I denote that using colors. So this red leaf is paired with this red leaf. This pink leaf is also paired with this pink leaf, and this blue one with this blue one, and so on. Okay, so basically what this is saying is that the solution of the nonlinear Schrodinger equation is expanded in terms of trees. If I look at the variance of the Fourier modes, this is expressed as a sum over pairs of trees, which are things that we call couples. Okay, a couple is a pair of tree where the leaves are completely paired to each other. Okay, and those serve as the Feynman diagrams for this book. So the couples serve as Feynman diagrams for this book. Okay, so let's talk about the difficulties of the short-time proof. Okay, so the first task is basically the idea underlying this diagrammatic expansion is that you're doing a diagrammatic expansion for the solution of NLS, and you want to identify leading order terms in this expansion and match them order by order with another diagrammatic expansion of the wave kinetic equation. Okay? And this can be done, basically, the step of identifying the leading diagrams in the NLS expansion and matching them order by order to the WKE expansion. This is a purely analytic task. It's quite tedious. It takes about maybe 50 pages, but it can be done. But the bulk of the proof is to show that all the remaining diagrams are lower order terms and do not disturb this approximation. Okay, so for this, there are 2 enemies that one has to confront. The first one is a factorial divergence in the number of diagrams, like the number of those couples that I showed you on the previous slide. Okay, so unfortunately, there are factorially many such diagrams. And if you can only show that those diagrams are bounded by some constant, which is basically order of delta to the n is the best such constant, where delta is the time interval of your approximation. Okay, so if you can only show that, then you're doomed to failure, because a series of the form delta to the n times n factorial diverges. Okay, so this is the first problem that one has to encounter. And you, as I said, you really cannot improve order of delta to the n, because the leading order diagrams in step one, they have size order of delta to the n. The second problem is that you have some diagrams that are diverging. Basically, there are some diagrams that can be equally as large as the leading diagrams, and in some cases, depending on the scaling law, they can even be worse than the leading diagrams. So unless those things cancel with each other, the theorem cannot be true. Okay. So this brings us to how to resolve those difficulties. There are several elements of that resolution. So let me just outline them vaguely in a way. So the first and most important element is a rigidity theorem that one has to prove, which basically tells you that even though there are factorially many diagrams, only exponentially many of them are large. Okay, so not factorially many of them have size delta to the n. So you really don't have delta to the n times n factorial, a series of that form. Because the diagrams that saturate the estimates that have size similar of delta to the n, they are really exponentially many, they're not factorial many. And for most of the remainder of the couples, you have much better estimates than delta to the n. You have estimates of the form delta to the n times L to the minus Cm. So you have a gain of L to the minus Cm, where n is large enough to offset the factorial divergence. Let's see how this happens. So the way this is done by classification to the couples according to this L to the minus Cm gain. And basically showing that the couples that gain L to the minus Cm, there are only order of Cm factorial of them. Okay? So why is this okay? I'll show you in the next point why is this okay. I just want to say that here, the proof of this rigidity theorem is based on solving a complex combinatorial problem on arbitrary large couples, which are basically, well, these are graphs. There are two trees paired to each other, where the leaves are paired to each other. And this is done using a deconstruction algorithm. But why is this rigidity theorem sufficient to offset the factorial divergence? The reason for that is that we can stop our expansion. Remember, a couple of slides ago, we expanded up to order capital N. We can stop this expansion up to, say, log L to the 5. And if we do that, then we have, for those couples that gain L to the minus Cm, okay, we said that there are Cm factorial of them. And this is something that is small as long as M is smaller than log L to the 5. So this is how you overcome this factorial divergence. There's also the other difficulty that I mentioned, which are those very large, or those large non-leading couples. So those have to cancel with each other. So these are, I just drew you over here, two examples of couples that could be arbitrarily large. So over here in C and D, there could be very large trees attached over there, and same for A and B. But somehow, if you switch or if you twist this diagram on the left to the diagram on the right, there's a major cancellation that happens between them. And this is something that one has to identify, and one has to even build a systematic way to identify those things. So basically, the conclusion here is that this diagrammatic expansion is something that it's an expansion that converges conditionally, but not absolutely, which is a big difference with the, for example, the Boltzmann case or the Lanford theorem, where the expansion converges absolutely. And then there's the problem of estimating the remainder term, which reduces to estimates on Feynman diagrams, but I don't have much time to go into that. Okay, so this is basically the ideas or the main ideas of the short time proof. So now we can move on to the long time result. So here the main difficulty is that every single series expansion that I talked about in the short time proof diverges on the interval, any interval bigger than delta, Okay, basically delta was chosen to be essentially the interval over which those series converge. Okay, so the first thing to resolve is at least it's easy to resolve the divergence of the expansion of the wave kinetic equation. So the wave kinetic equation, you know the solution exists on the interval 0 t star. You know that the solution is analytic in time. So, okay, so what this tells you is that you can split the interval 0 tau star into sub-intervals of size delta, where on each interval p delta and p plus 1 delta, the solution of the wave kinetic equation is given by a series expansion, but with initial time given by p delta. Okay, so this at least this resolves the divergence problem for the wave kinetic equation. Okay. But of course, this does not resolve the divergence problem for the NLS expansion, which is the far more important and more complex expansion, which at this point, we really do not know whether it converges outside this interval 0 delta. And the reason why we don't know that is that even getting to the time 0 delta, which is really according to the time scale of NLS, it is 0 delta times T kinetic, which is delta over alpha squared. This is a very large time in the eyes of the nonlinear Schrodinger equation. And the only reason we were able to get to this time is because we were assuming that the initial data are random and independent, which is something that is true at time 0, but is definitely not true at time delta. If I assume that this is something that is true at time delta, 2 delta, etc., I just repeat the proof all over again and get to time t star and we're done. But the main point is that the Fourier modes are not independent anymore at time delta. So naturally, so this slide is really about what you do if you follow your nose and if you want to extend to longer times. Okay, so then you realize, okay, I don't have independence at time delta, then maybe I should try to measure this lack of independence at time delta. How would I measure this lack of independence at time delta? This is an idea that is very much well researched in statistical physics. You look at the higher moments of the solution, or more precisely, objects that are called cumulants, which are linear combination of higher moments. Things that, like higher moments are, what I mean by that are, you had of TK1, you had of TK2 bar, you had TK3, you had of TK4 bar. For example, this is the fourth moment. Okay, so this is the fourth moment. The fourth cumulant is something that is obtained from this fourth moment by subtracting lower order moments of it. And if this cumulant is small, then this would be an indication for you that the system is close to being independent. It would be completely independent of if all the cumulants of order bigger than 2 are 0. Okay, so these cumulants are really a very good measure of the independence of the Fourier modes. Okay, so the cumulants are basically very much related to moments. So think of moments over here. And remember that when I was looking at the second moment, which is the expected value of u hat at k, u hat k bar, I ended up with couples of trees. These are 2 trees with the leaves are paired. If I'm looking at higher moments, I will end up with what we call gardens of trees. So something like that. So these are more than 2 trees, several trees, but still all those, all the leaves of those trees are paired to each other. So the color, this is denoted by the green color. Ignore those numbers for now, but that is attached actually to those. Okay, so the strategy. So now this is the first slide was really what you do just by following your nose. The second slide is when things start to become intricate and where difficult choices have to be made. Okay, so the strategy is we need to set up an ansatz for the cumulants to prove that at later times, at time maybe, so the strategy is that to prove that at time delta, okay, the cumulants are not zero. In other words, the Fourier modes are not independent, but they are close to being independent. In other words, the cumulants are close to being to zero. And you try to do that, the same thing at later times delta to delta, etc. So you try to set up an ansatz for the cumulants, basically, and maybe we can try to prove it by induction on the time layer, so on those time steps. And in such a way that those estimates deteriorate successively as we go in time. However, one thing that one realizes early on is that just by imposing an estimate ansatz, just by saying that I want the cumulant to be, the fourth cumulant to be less than L to the minus some power, sixth cumulant L to the minus some other power, just imposing an estimate on those cumulants is not sufficient, is not enough. And indeed, one needs to track the information that is carried by the structure of the cumulants. So in other words, we need to track basically the problems that we really need to keep track of the time oscillation of those cumulants, not just their absolute value estimate. And to do that, we introduce what we call a structure ansatz that not only retains an estimate on the cumulants, but retains the structure of those cumulants. And this structure ansatz is basically given by those Garden expansions of the cumulants. Okay, so this diagrammatic expansion turns out to be subtle, and the reason for that is that again you have a divergence problems that you cannot really expand those Garden expansions all the way to time t equals to 0 because this will lead to a divergence, actually a bad divergence. Instead, one has to do a partial time expansion for the cumulants, and this leads us to what is called the canonical layered gardens, and this is what was really represented on this slide. So this is a layered garden is a garden without those numbers over here. So those numbers denote the layer basically where this node emerges. So the layer means the time step over here. That's what we mean, the time layer. And those canonical gardens are sort of special gardens where the layering of the nodes has a specific rule that I will not go into today. Okay, so this is what we call canonical layered gardens, and it turns out that this is the right expansion to make, and this is the correct ansatz, and the proof will then proceed by induction argument on the number of layers to prove that structure ansatz. So my last slide is about future directions. So of course, the natural question that probably is on everybody's mind, whether this would allow us to extend those ideas to the Boltzmann equation and get a long-time derivation of Boltzmann equation and hopefully a final resolution of Hilbert's sixth problem. This is something in progress with Yu Deng and Zaher Hani, who is at Michigan. And then another very interesting future horizon is this link that I talked about very briefly to the world of turbulence, which is basically accessing the turbulence aspects of this kinetic theory. And for that, we need to have a good analysis of solutions of this wave kinetic equation, which is something that is very rich and at the same time very poorly understood. There are some pioneering works of Escobedo and Vasquez and some works that recently came up, but there's a lot to do here, particularly that is important in order to understand energy cascade behaviors for nonlinear dispersive equations. And I'll stop here.
Thank you very much. So, questions or comments?
I noticed that in the theorem in 2021, in the slides, there is a condition about the rotation of eta the eta k omega. It's assumed that it's rotationally symmetric. Is it important in the proof?
Yes, very much so. I mean, this rotation symmetry, it's an interesting question, how much one can relax that. But this rotation symmetry is, at least it has been quite important in the statement of the physical theory. because this is related to something that is referred to as phase randomness. So what we're taking is that you're taking the Fourier modes, you're taking essentially the modulus of the Fourier modes to be almost something that is deterministic, and then you're randomizing the phases in a certain way. And this phase randomness, the fact that you are taking the phases to be random, is exactly what, if you want to state it in mathematical precise terms, is the statement that eta k is rotationally symmetric. That really your initial distribution does not have a preferred direction of the phase. It sort of randomizes all the phases of the Fourier modes. So this is very important in the proof. How much it can be relaxed is something that is interesting, but I don't know what the answer. I don't know if you think you have thought about that either.
Not too much.
Yeah.
Okay. Thank you.
Other questions or comments?
I have a question. What's the role of randomness in this theory? So if we assume that actually we don't have a random variable, there is eta k is not Gaussian. Is deterministic. Would this result be true?
No, not really. I mean, the same, even Boltzmann's theory would not be true deterministically, because you can start at time t equals to 0 with all the particles in the room in my hand and vacuum elsewhere, and this is a very legitimate initial data. And then as time passes by, you probably won't get the solution of Boltzmann equation. You cannot use fluid equations in order to solve for the fluid velocity. So randomness is absolutely crucial for those things, and it's for that reason randomness is absolutely crucial in statistical physics in the first place. So, and the same thing happens in the wave theory. We know that there are solutions of the wave kinetic of the nonlinear Schrodinger equation that do not behave according to that kinetic wave kinetic equation. There are solutions that are quasi-periodic in time, that are clearly not cannot be described by a kinetic equation. So the randomness is really crucial in any kinetic theory.
Other questions or comments? No, Mustafa.
You got me. So in the very beginning of the slides, you talked about two phases of limiting procedure. Second one was hydrodynamic limit. That gives you the fluid equations and all that. But the first arrow was kinetic theory, not wave kinetic theory. So assuming this you're working for the first arrow where we have now wave kinetic theory instead of Boltzmann kinetic theory, how does the second arrow look?
Yeah, that's a very, very good question, actually. So, so basically what you're saying is that we have this nice diagram in the particle setting. The question is, what would be an analogous diagram, particularly what would be an analogous limit over here in the wave setting? And this is something that doesn't seem to be very well understood yet. Okay, so we have this first arrow in the wave setting, and people study and get a lot of leverage out of this wave kinetic equation. Depending on the field of science, it might be because of Zakharov's connection to turbulence, because of that, but it might not be because of that. People just study those kinetic equations and their solutions. But I have not seen a good treatment of some hydrodynamic limit in that setting.
I think formally for the inhomogeneous quantum Boltzmann equation, I think there might be hydrodynamic limits.
Yes, that's true.
For the inhomogeneous, pure wave kinetic equation, I don't think it has been studied. For the homogeneous equation, I think the behavior is quite different from hydrodynamic. There will be kind of formation of condensates and things like that. It's something different for the homogeneous.
Yes. So in the homogeneous setting, so the only place where there's some semblance of this line is in the case of the inhomogeneous quantum Boltzmann equation. Yeah. And that's a good question to investigate in more general.
Other questions or comments? And let's thank Zaher again for an excellent talk.